Well, so after that, I'd like to introduce our speaker, Dr. Darren Holt, who's recently became ASCE fellow, and he's a licensed professional engineer with expertise in non-destructive testing and advanced digital signal processing techniques used for evaluating civil structures. He's licensed in 48 states, District of Columbia, and Puerto Rico. His academic credentials include a Bachelor of Science in Civil Engineering, Master's focusing on structural mechanics, and a PhD concentration in computational and applied mechanics, all from NCSU. So, feeling at home. Yeah. And it's pioneer in development and implementation of dispersive wave propagation methods used for infrastructure assessments and the author of many publications and field manuals. As an entrepreneur, Darren was a founder of the FDH family of companies that offered non-destructive testing services throughout the Western Hemisphere and subsequently grew to employ over 300 persons with offices in 6 US states. So pretty extensive background, so a lot of knowledge to share. So it's definitely our pleasure to have him here. So should be able to
just the arrow key.
Yeah, I think that should work. I think. Yeah.
We'll find out.
Yeah, I know. Let me
Hey, how's everybody doing? I know you're doing fine. You're doing great. It's good to see several familiar faces in here. And am I talking too loud or not loud enough? Doing okay? Jim, you can even hear? All right. And for those of you online, I wish I could see your faces because I'm quite sure I know several of you in there. Appreciate ASCE having me here. And I recently became a fellow. So this is one of those presentations that for me is fun. I'm not trying to drum up business and I'm not trying to be commercial and sell something to somebody or services to someone. So, but there's a downfall to that because I didn't have anybody or a media department to put my presentation together. I had to do it myself. I used to have all these folks that would put slides together for you and make all pretty shiny things. Not today. So let's just talk about it. I got a few action photos. I've got a couple of slides with 3 or 4 slides with some mathematics on it, or really some digital signal processing on it. And we'll just go from there. Now, non-destructive testing is a big area. I mean, it's huge. Non-destructive testing of the civil infrastructure is even bigger. And so I cannot mention or go over all the different topics that are meant to go over. So I'm going to hit on 3 or 4 of my biggest ones that I've used over the years. And this is an open, easy conversation. Raise your hand, yell it out, scream at me, do whatever you want to and get my attention. See if I can answer the questions. So with that, yeah, I could probably do it from there.
Yeah, there we go.
There you go. Yeah, I'll be fine. I'll do good. All right. First, as Nick and Patrick were saying, I was very fortunate when I was in college. Myself and 2 other professors, Dr. Robert Douglas and Dr. John Fisher, and myself started a company, FDH Incorporated, subsequently FDH Engineering Incorporated, for the purposes of doing non-destructive testing of bridges, buildings, whatever we could do. And my personal background, as some of you know in here, I worked with Dr. Douglas and the late Dr. Vernon C. Matson and Dr. Fisher, and we were able to come up with a technology to inspect bridge piles and structural pilings in general. And I'll mention those as we go on along in here. As far as the logo on my print presentation, I ain't got a logo anymore. So I put up the ASCE fellow. And I just came from the firehouse. So obviously I'm dressed in my fire station stuff. So it's been 42 years in the fire service as well. So with that, first thing I want to talk about briefly is pulse echo techniques. How many have been familiar with pulse echo testing for investigating existing structures? I know Jim has, and I suspect David has too, a little bit. The next one will be structural pile foundations. What do we do when we think they're damaged, or what do we do when we don't have records of how deep they are in the ground? That's a big one. That's a really big one, because how many times do you go out and you don't have as-built drawings for a structure? You got to figure out what's there. Structural scanning, I classify that it can be either easy or hard to do. In other words, what kind of rebar is within the concrete, because that in turn determines capacity, as you know. And the final one was a technology that I was able to put together for dams for the U.S. Army Corps of Engineers, and I'll mention that. That's what I call the nightmare stuff. That's big boy stuff. That is big structures. And we did a lot of work for the Army Corps of Engineers, and they're still doing work for the Army Corps of Engineers. But the number one thing is not knowing what your as-built structure is can be a costly mistake. Some photographs I have over the years when I was in business that I can't show because I was under non-disclosure, not to show my structure being on the ground, but this is one of them that I could show. You'll see a lot of lattice towers in here, basically because it's a structure you can see and it's a foundation you can see. And for the most part anyway. This particular structure, as you can tell from what looks like the weather conditions, it was on the ground from an ice storm. How often do we design for half-inch radial ice? Well, what happens when you get to 1-inch radial ice, or whatever the case may be? This particular structure was on top of a mountain in northern Idaho. Why most enjoyable? One of the most enjoyable projects I've ever had, because I got the phone call on a Sunday night saying their tower was on the ground. But the problem was, and that's not a big problem in general because it means you're out of the cell phone service. But the problem was E911 or Enhanced 911 was on that tower for the whole county and the whole area really. So they had to get it back going real quick. And I told them I could be there by Tuesday or Wednesday because of how remote the area was. They said, no, you need to be in Idaho when the sun comes up on Monday morning. And so getting there was a chore. And as you can see, there's a red snowcat in the background. Had to go get up there and get there. So it was a structural failure. And as it turns out, the owner of the tower did not know anything about the site. They didn't have the structural steel sizes and they didn't have the foundation sizes. So it was basically a big unknown. Okay, what is non-destructive testing? Well, technically, and I can read it verbatim just like y'all can, NDT is any set of techniques that allow inspectors to evaluate materials, components, and systems without causing damage. In other words, what do you do without tearing it up? We don't want to tear it up. If you got a structure that you want to remodel in your business for your clients, you always ask them, have you got any as-built drawings? All the time. Do I go to archives and can I find them? Yeah, not really, not all the time. In our business, Jim is very familiar with Jim Billups over there. As-built drawings were a gold mine when we could find them. They were just not always there at all. Well, one solution, and there are many solutions, from visual techniques to hitting something with a hammer and listening to how it vibrates, that'll tell you a lot about what's inside of a structure as well, believe it or not. But one solution is wave propagation testing. And what I mean by wave propagation testing, in simplicity, in its fundamental form, is if you walk up to a puddle of water or a swimming pool, you drop a rock into that swimming pool, you see the ripples that propagate outward from where the rock entered the water. That's wave propagation, just like the beach, except in solid materials like timber, steel, or concrete, those ripples can travel at 6 and 7 times the speed of sound. And we have to be able to capture that motion. What that does for us, if we can find where those ripples get to the edge of a foundation, turn around and come back, we know how fast they're traveling because we can measure it. We can tell you how long or how big that structural component is. And if there's damage within it, and I'll show you some pictures of that, we will be able to tell you where the voids are. Not little bitty voids like missing aggregate. I mean a big void, a big hole. Maybe concrete wasn't, placed appropriately. But my forte was foundations, first and foremost. So I always like to start with the foundations portion. Foundations do fail. Photograph on the right is a drilled shaft. As you can tell by the corrugation they put in the top layer of soil to keep it steady while they drill deeper and deeper. But somewhere between the end of that corrugation and the concrete side, it failed. It cracked. Strong wind came along, pulled the foundation out of the ground. You don't see that very much. How many's ever seen a drilled shaft that's been pulled out of the ground? It just don't happen, does it? So this one happened. And the question incidentally became, was it deep enough in the ground so it wouldn't pull out because it had number 9 bars that ran longitudinally down through it? Well, as it turns out, long story short, they ran out of the length. They didn't order the proper length of rebar, so they put rebar on top of it and spliced them all. Don't really do that. That's not very good. This photograph doesn't show up quite as good on this screen, but one on the left is what we call a dead man anchor. It's a chunk of concrete that's in the ground holding cables from a broadcast tower. Wind comes along, the foundation pulls out of the ground. Pretty simple. Pretty simple reason why it happened is just could not carry the load. So what do we do first? We got to look underground. This is Jim upside down looking in the hole. Except I think those boots are a little bit too small for you, Jim. And it's a small hole too, right? So you have to look underground, but let's do it non-destructively. As I mentioned, pulse echo techniques. Some of you are very familiar with it. How many, this is a fun, raise your hand. How many have ever used PIT or PET, pile integrity testers, pile echo testers? How many people have worked in pilot? You have? Okay, cool. The PE techniques, or the pulse echo techniques, are very good for shallow foundations, concrete mats, pads, drill shafts, auger cast piles. When you basically want to know how much concrete is there, how deep it goes into the ground. In essence, and I'm only going to hit this one somewhat briefly, and don't you love my little schematic here? It looks like I may have gotten my daughter to draw it for me. But I don't have anybody do this for me anymore. What you're looking at is soil, concrete, transducer, impact. And I've got some action photos in the next slide to show you. But basically, you hit anything with an impact device. An impact device is a high-tech calibrated device that you can buy from a manufacturer, and it costs about $4,000 or $5,000. Guess what I always did? I went to Home Depot. I got the prettiest yellow 3-pound hammer you ever seen in your life. Perfect. Works 100% of the time. Create an impact. Once you hit the surface of that material, you cause an indentation in that material. You cannot see it with your naked eye, but you can see it electronically. That indentation then travels throughout the material. Goes down to the bottom of the concrete. It hits the bottom of the concrete and it reflects and turns around and comes back up. Pretty simple. We know the speed of sound or wave propagation in concrete. We can come over here to our computer and say, that's where we hit it. That's where it came back from the bottom. That's a total travel time. We know the velocity. Multiply it by t, divide by 2, you got the depth. It's pretty simple. That's why I call it the easier methods. Incidentally, they use these techniques for inspecting everything from concrete mats to floor systems in warehouses, even to rotor blades for gigantic windmill turbines. I've seen them do it, and I've been a party to it in South Dakota many years ago. They got a big device that just goes along, hits the surface, gets the thickness of the composite materials. So It's used a lot. It's used about everywhere you can think of. And this is a photograph of just a technician doing a test, transducer hammer, and all they're doing is creating this methodology here. Cost-wise, that's the cheapest test to do. It's quick, it's simple, it's easy. Just have to know what you're doing and how to analyze the data. And there are plenty of devices out there on the market now that are built into the computer system. You strike it, it'll say it's 3 feet thick or it's 45 feet thick, and you can move on about your work. But do it 4 or 5 times if you're out there doing it for a living, and make sure you can reproduce the results multiple times. And what do you do if the concrete is buried? Well, what you can do, top left photograph, is you come in here and do it the old-fashioned way. Drive a grounding rod in the ground and find this buried pad. You got to find it first. If it's underground, you don't know where it is. And you mark it off. You find it, mark it off. Then you can come over and drill you some holes or drive you some rods, put a transducer on your rod, and take a third rod and hit it with an impact device, a hammer. These are 8-foot grounding rods that you can get from Home Depot. And it creates the pulse in this buried pad. And you can measure the waves with these transducers, and you can get the thickness of the pad. That seems like a lot of work. What can you think of looking at that diagram that you could do else? Yeah, photograph. Bottom left photograph, test the pier. That's exposed here. You test the pier, you're generating waves that go down to the bottom and back. You get this dimension. And then you can drive your rods and get that dimension. So you got the thickness of the pad. Does that sound pretty simple? Ain't nothing that's simple.
We've got that joint. It could be.
That's exactly what I was fixing to mention.
Okay.
You're doing good. You're thinking. Let's have fun here. I hate joints. You know, contractors love to dig this wonderful cubic hole or square hole that has a deeper depth to it. Pour concrete about 2 feet thick. Let it dry a little bit. They put the little rebar sticking up, and they come in and put a what I call a can. What is a sonotube or something down there? And then backfill it with concrete. There's a joint. What are you gonna do now? Well, that's why we had at my old company, we had to come up with this system, because we were finding out this was basically a cold joint. If they poured it all in one monolithic pour, we could have got the full depth without ever having to test using this rod method. So somebody comes in there for your businesses and say, I'm going to test here, I'm going to drive a rod here, and I'll give you pad thickness. No, they're going to find out. They're going to get this thickness of the pier, and they're going to find out the pad starts right there. And so how thick is the pad? But in reality, how thick do these pads normally have to be? I mean, it's just surface area pulling on the soil. I mean, what, a couple feet, 18 inches? How thick have we seen them before, Jim? I have seen a pad that was 4 feet thick. I didn't believe my numbers. I didn't believe my calculations. We dug it. We come off to the side here, dig a hole, and drive a rod under it. Sure enough, it's 4 feet thick. Only thing I can think of is somebody wanted to sell some concrete. And back then, it was only 350 cubic yards to buy it and place it. And what is it, about $1,800 a cubic yard now? So, but anyway, pulse echo. Hit something with a hammer, sound goes down, sound comes back. You know how fast that sound is traveling in concrete or any material you're testing, because you can look it up. Incidentally, in concrete, sound travels at 12,500 feet per second for normal strength concrete. Mach 6, Mach 7, somewhere in there. That sounds familiar. So it's really, really fast stuff. For those of you who are still in academia, I love this part when I explain it to someone. If I hit the top of this pier, because I'm testing the top of this pier, if By the time my hammer hits that pier, and my hammer bounces off that pier, that sound wave has already bounced up about 10 or 15 times by the coefficient of restitution. Love that stuff. Dynamics was my thing. Didn't everybody love dynamics in school? Yeah, I know you did. Come on. But anyway, the point of the story is, if I hit this with, let's say, my little fella here had a 50-pound hammer, and this is a 4-foot thick or 3-foot thick concrete pad, and I drop that 50-pound hammer on that concrete. Before that hammer bounces off, that event I'm looking for, that wave going up and down, she's already bounced 100 times because of the weight of that hammer. So how do I get around that? I get that very expensive calibrated impact device from Home Depot called a ball peen hammer. It's much lighter than a 3-pound sledgehammer. This is all, it's impact. Impact is an art. It is a science, yes, but it's an art. How lightly can I hit something and create a signal? Okay, that was pulse echo. Now here's the stuff I went to school for, structural piling. Prior to 1994, 92, I don't believe we couldn't find any reference to this method of testing ever being used. Thus is the reason the NCDOT and the Federal Highway Administration was very graciously funded a project at NC State that I was able to not go to work for a living. I could stay in school, because if I got out and worked for a living, I had to have responsibility. So I stayed and got a PhD. It's for driven piles, timber, steel, or concrete, and actually for auger cast piles or our drilled shafts. And we've all seen pictures of bridges. How many are in the bridge industry here? Is that it? Just one? Come on. Oh, come on. Anyway, I love bridges. I love old bridges. Concrete piling, hard to test. Why? Because there's a pre-stress in most cases. But the larger they get, 24 inches are hollow, 18 inches are soft. There's a switch over there. When I say, I mean square size. So when I used to test concrete piling beneath bridges that were 24 inches on the side, I always knew that there was a hollow section in there, and everybody knows why it's hollow, because it doesn't weigh as much. You don't need all that material inside. But my favorite material is timber. Love timber. It's old. It grew. It's nature's material. I'm not very green, I'll admit it, but I just love timber piling. It rots. It just breaks. It splinters. It does all the stuff you don't want it to do. So I enjoyed working with it. Question is, how can you tell how long these piling are? This bridge is in South Louisiana, still there. And it was built so long ago, there's not even guardrails on the bridge, I don't believe. No guardrails. But the question was brought up to the highway department. They call it the DOTD for Department of Transportation and Development in Louisiana. How deep are they? And the DOTD was like, why do we care? It's been there for 60 years. Well, in 1989, was it 89? The bridge in New York failed due to scour. All the water came rushing down and washed out the embedment depth of the pile, or the soil around the piling. Bridge failed, some people got killed. So scour analysis became the big thing in the 90s and the early 2000s. So, and as of the time when I left the industry, I haven't left the industry, but when I'm no longer working every day, there was 101,000 bridges in the United States. They had no idea how deep the foundations were in the ground or how deep the piles were in the ground. And that's a lot. They're still working on them, by the way. So that's what we want to know. We want to know how deep it is in the ground so we can calculate how much erosion can occur before the bridge goes bye-bye. And incidentally, the capacity as well. So how did we do it at the Big Red Wolf Pack? We came up, And Bob Douglas, my professor at the time, who's since passed, he said, I have an idea. I'm very young, but I have an idea. Top left photograph, schematic superstructure, piling beneath the superstructure. Up until 91, 92-ish, the way to test, non-destructively test a piling that's sticking out of the ground was to hit it on top with a hammer using pulse echo. Wave goes down and up. Pretty simple. What happens when you put a superstructure on top? No luck. Can't happen. So there have been a few DOTs that would drill into the bridge deck to put transducers on top of the pile and hit it on top and create a pulse echo wave going up and down. Totally destructive. Long time, very costly. So what we did, we came in here and said, let's put transducers on the side of a piling and hit it on the side because we can get to the side of the piling. So what happens when you take a rod, or just a rod, that's all a pile is, it's a rod, it's very long compared to its dimensions, its circumference, or its square cross-section, I should say. If you take a rod and you hit it on the side, what are you creating? What kind of wave are you creating? It's like a piano string at that point. You're creating a bending wave, a flexural wave. So if you have multiple transducers on the side of a piling, strike that pile with that high-tech calibrated impact device that somebody's going to charge you $4,000 or $5,000 for that you can get at Home Depot, you will create a signal like this. The blue graph is the very first transducer. Wave is going down, it hits that transducer first. The red graph, it's the second transducer because it's going down. So you see there's a lag in time. I didn't put the third one up here because it would just clutter up the schematic. Flexural wave goes to the bottom, turns around, comes back. The red wave is now ahead of the blue wave in time. That's how you know it's coming from the bottom. Signal going down, signal coming back. Get the link. That sounds easy, doesn't it?
If you're embedded in rock or anything like that.
You can. I'll show you how to do it in rock. Can't do that in rock with this. Well, here's the problem that we had to work on at the university for 2 or 3 years. 3 years, actually. See my little timber pile here that I pulled from an old presentation from like 20 years ago? You hit it on the side, you create flexion. It does happen. You cannot see it with your naked eye, but you can see it electronically. The center line of that piling bends. That's flexion. The wave moves back and forth up and down the pile. This flexural wave makes pile testing much more reliable because flexure doesn't, and shear motion doesn't matter about water. Most of these piling are in water or they're in a wet condition. Pulse echo, it hates water. Forget it, hates water. Flexural waves, love water. Water basically has very little to no viscosity and doesn't carry shear motion. Here lies the problem that we solved at State. See the signal in the bottom photograph? That's just a representation of a signal created by this hammer. As this signal travels down the piling, turn around and comes back, all the little frequencies separate from the signal. In other words, the easiest way I know to describe it is if I hit a piling and I create a wave, flexural wave that's 12 inches long. When that flexural wave has traveled 3 or 4 feet, about 7 or 8 feet long, when it goes to the end of that piling back, it's 20 or 30 feet long. That's dispersion. If you think about a bunch of cars on the belt line or at a stoplight, they're all stopped. Traffic light turns green, the first cars pull off. They don't all pull off in one mass, do they? They all pull off one car at a time. A bunch of those cars are separating each other. separating from one another. That's dispersion. Quite frankly, the pile testing at State was more digital signal processing and mathematics. This field test setup we had it done in a month. Testing in the field was pretty simple. This is what it looks like in real life. Concrete pile, transducers, high-tech calibrated impact device with a yellow hammer this time, yellow handle this time. Timber pile, transducers on the side. What are we hitting it with there? No? What's that? It does look like a toilet float. It's a bocce ball. We drilled a hole in top of that thing and put a little rod in it and screwed it down tight. It's a bocce ball. Now, why would I hit with a bocce ball versus a 3-pound Home Depot hammer? I don't get anything from Home Depot for talking about the hammers, by the way. Shape of it, bingo. This hammer is wonderful. It's made of metal. It's always going to hit in the sweet spot when you hit something. That's why it's designed like that. Metal hitting timber, it's very noisy. Well, this is noisy too, yes. Do not get me wrong. Metal hitting concrete, very noisy. But when you hit timber with a metal hammer, you're crushing everything beneath it. So we said, why not a bocce ball? Remember I said impact was an art? A bocce ball, you're always pretty much going to hit on the sweet spot. The number one impact device that I don't have a photograph of, and I searched and searched and searched. You remember my perfect impact device? I found the perfect impact device. You don't remember. Jim didn't go to the field a lot. Bowling pin. I can't tell you the number of bowling alleys I would visit when I go to a city doing pile testing for highway departments. They always had them. They were cracked or broken a little bit. They were going to throw them away. And no. Give me your bowling pin. No matter where you hit on a bowling pin, it's the sweet spot. I always enjoyed it. Baseball bats are not even as good. If you can make a baseball bat, and I'm sure they do, that's shaped like a bowling pin. Yeah.
What's the sweet spot?
Have you ever taken, I don't have one, take a pencil or a pen and bang it on the edge of your table or edge of your glass? There'll be one spot, you'll feel the vibration in your hand when you're banging it. You'll feel the vibrations here. But once you hit what's called the center of gravity, the sweet spot, you feel no vibration in your hand because all the energy is being transferred to the glass or the edge of the table. That's the sweet spot. Baseball players hit balls. They hit ball. Now, I'm not a baseball player, and I don't do research for baseball players, but sorry about that, folks online. I know that's making you sick to look at. Sorry, I dropped it. You hit a baseball with a baseball bat. Have you ever noticed the people that hit the home runs consistently? They're not the biggest people out there on the field. They're the folks who know where the sweet spot, or they're just mentally programmed. They hit that baseball in the sweet spot. Speed and sweet spot. The speed is your momentum. You hit that sweet spot, that's maximum energy transfer to the ball. It's got to hit. I hit a home run one time, and I never knew I even hit the ball. That's how perfect I hit it one time when I was in Little League. The folks like what? Again, I don't play baseball. Hank Aaron and those folks, they always hit the sweet spot. But try that sometime. Take a broom handle at home. Hit the side of your deck or the side of your table. You'll find up and down. Just move it up and down. You'll find that one spot. Underwater testing, did a lot of that. I didn't have any underwater photographs, so I thought they'd put that in the presentation. Remember, bending waves or flexural waves do not depend upon water, so we could test them all day long in water. We've had a dive team that worked with us for years, and they didn't work as our employees. We contracted them for years. They did our underwater testing. This is your technical part. That is a time record of a flexural wave in a pilot. I think it's 10 minutes. Amplitude, time. 6 microseconds per individual point. So if you do the math, 6 times 10,000 points, 60,000 microseconds is the entire time record. How long is that? 600th of a second or something like that? This is what we had to deal with at the university to figure all this out. These were our records. How can we filter these records to get the information out of them? There is a mathematical technique still used by my old company to this day for everything called the short kernel method, the SKM. It's a digital signal processing mathematical tool. We wrote it ourselves at the university. And when you do that, there's what the signal looks like after you filter it. You can't, it's hard to tell in this lighting, but the blue line is a transducer closer to the impact. The pink line or the reddish line, transducer below that one. Signal goes down, signal comes back. Signal's going down, they're reversed here, signal's coming back. So that's how we knew that we were getting the end of the piling. And we simply had to calculate the velocity and measure the time between these peaks. And we get the length or how far the wave is traveling. Luckily, when it was all said and done at the university, we were within plus or minus, really we were within plus or minus 8% of actual known pile lengths, but we advertised 10 to 15, just to be on the safe side. We're engineers. Throughout my career, yeah, I found a lot of piling that were supposed, everywhere we went, I had to do a test for the owner, which is what you should do. Make sure the owner wants to make sure you know what you're doing. That was it wasn't as easy as hiring an FDH engineering. You come in, you do your little engineering and you stamp something with your PE seal and you move on. You're doing something that's never been done before. So they always put you to the test. I wish I had photographs of it, but I was told I could not show photographs, so I've never showed them. But there were some pilings in a certain state down south that they were supposed to be 70 feet long in the ground, 8 feet above ground, above the mud line, and 62 in the ground. I was getting 40 to 50 and created a big ruckus. I wish I had photographs. For those of you online, I really wish I did. And they came back. They had fired us that day. We couldn't do it. We couldn't get how long their piles were. I came back to North Carolina, deciding I'm going to go be a real fireman, I guess, for a living. Well, a couple of days later, I get a phone call. You need to come back down here. We got back down there. All my buddies that were around me in this meeting, they were looking for windows to jump out of. Okay. I was left holding the bag. As it turns out, they started crawling back in the windows when they found records, real records from the contractor. The piling had been ordered at 70 feet. They had been put in the ground at 70 feet. What they did not take into account is the pile driving records were showing 500 and 600 blows per foot. What do you think happens to a piling when you beat a timber pile 500 times a minute? You crush it. Boom. And as a result, they pulled it out of the ground. And there wasn't any piling below much. There was one piece that was 50 feet. The others were like 38 to 42. That's what they could get out of the ground. And you can pull a pile out of the ground, by the way. It takes a lot of effort, but you can do it. So anyway, needless to say, I spent the next 2 years of my life in that particular state doing bridges. Loved every minute of it. I really gained some weight too. I mean, they had good food. What do you do when the piles are out of sight? This gets into your question about rock anchors or piles or anchorages that are in rock. You can do what I'm about to show you for rock as well. I've got a diagram of that. This is a bridge. I quite frankly don't remember where this bridge was, but it's on footings. Below the footing or piling. I can't do a flexural wave test because I got to physically touch the pile. What am I going to do? Well, what about, here's the pile cap, here's the piles, we drill a hole in the ground, and we drop a hydrophone or a geophone. I preferred hydrophone. And we create a signal Oh man, it didn't show up on there. But there's a hydrophone. It creates a signal that goes out, hits the piling, and comes back. So I have a record of hydrophone data. In other words, I'm listening for the side of this piling, and I'll show you the data on what it looks like in a minute. So the idea is you've got to drill this hole deeper than what you think the piling is. That way you can guarantee your sensor is going below the tip of the pile. It throws out a signal. It hits everything in the soil between this sensor and that pile, but the strongest signal will come back from the pile. Signal hits it, turns around, comes back, we capture it. And I have a record to show you that. This can be done on exposed piles or buried piling. And all you're seeing right here is just simply, we got a hole in the ground with a drill rig, dirty messes, and hit piling with that calibrated impact device, except we're doing a little bit harder and heavier. Dropping the transducer. This is actually a transducer cable going into the borehole. And over here, same thing. This is an abutment supported on piling. You drop the sensor in there. And I wish I had a picture of the other little fella that would go over here and just hit the abutment with a hammer. He was high tech. I'm telling you, we had a ball with this. But what do we get when we do that? It's quite simple. I thought it was ingenious. Oh man, there's your light for causing a problem there. Envision depth. I'm sure those online can see this. These graphs a lot easier. Depth below ground. We drill this hole to 150 feet. And this is basically time per point, like 5 microseconds per point. We captured 8,000 points per record. Then we plotted them all up. And is there any way to, Patrick, is there any way to, yeah, dim the light over here? Yeah. Okay. Anyway, wish you could see it. But as we're dropping the transducer down the hole, and it's throwing out a signal, capturing the reflection. That doesn't do any much good. It shows a linear relationship until such point that transducer goes below the pile tip. And there's a change in the arrival time of that signal. That change at the tip of that pile, these particular piles turn out to be actually 110. So below ground. So we were very pleased with that result. This was actually a test that the state DOT for the students to see if we could actually do it. Answer your question, Patrick. This is the same thing that we would do for rock. Drill you a rock hole in the rock. If you have rock anchors, and I got a schematic of that, and do the same type of test. Looking for the bottom of the rock anchors. Structural scanning. Look at my time. In other words, what kind of rebar is in your concrete? Can it be done? Yes, it can be done. You need to know what's in your concrete for capacity and strength. It can be done within reason. I'll explain that in a second. Much better. This is us doing some investigations of some drilled shafts. They wanted to, the client wanted to know how much rebar was in it, the size of the rebar, et cetera, et cetera. This is a structural scan device that emits a 2 gigahertz signal. It's ground penetrating radar for concrete, except GPR is 200 megahertz. Structural scanning in concrete is 2 gigahertz or higher because you're looking for very small stuff like rebar in a big concrete block or chunk. I never made this equipment. This is commercially available. I think FDH still owns a couple of them in their shop. We use it every day, everywhere around the country. People wanted to know what was in their concrete. This is a tool. What we were able to do is come out and say, that was your drill shaft, Mr. or Mrs. Client. These are your rebar, and this is your size of your rebar. Now, how do you think we got the exact size of the rebar off a 2 gigahertz signal? We drilled a hole. We knew where the rebar was. We can find it all day long. Technology is not quite a technology is to the point it can estimate, but I don't want an estimate. Is it a what, 7 or 11? I want to know it's a 9. I'm an engineer. I got to know. So we drill a little small hole right to the top of it, measure it. And we knew the signal or from all of them, they're all the same. This is a tool too. Did the same thing in concrete pads. This is the raw scanning of concrete, looking for a rebar cage. This is after cleaning it up a little bit. And this is after putting all the information together. We're able to come up with that. How did I know it was a number 8 rebar each way on 8-inch center? 8-inch center is easy. Where it started, where it ended was easy. How did I know it was a number 8? I drilled a hole. Okay. So, but you drill enough holes, you get to where, okay, this is data from Oklahoma City in somebody's backyard, and this is data from Texas. Well, they all look the same, and if you overlay it, it's an 8-inch bar. It becomes just putting it all together. And that's what you're looking for. Huh?
I mean, I'm sure by now that when you buy a system, because we've had a lot of subs.
Yeah.
True. Is it?
No.
They can all consistently tell the bar size.
Yeah. It might. No, wait a minute. You mean the people you hire, can they consistently tell the bar size? No.
The signaling and the feedback getting from the equipment. It should be consistent.
It should be consistent. Yes. You've got, and that's my last slide in here at the end where I'll show you that you got to hire people who know what they're doing. This is what you're looking for. And again, I'm sorry I didn't know the lighting and everything, I wouldn't have made it a white background on some of this stuff. Drawings, files, rebar, etc. That's what you're looking for. That's what you want to know as an engineer, right? Absolutely you do. Scanning, more scanning. This happened to be a tower. Somebody in their infinite wisdom, well, I know who did it. They put in 3 additional legs, which were PVC with post-tension cables and backfilled it with grout to give the tower more strength. Spend as much doing that as they would have building a new cellular telephone. But the reality is, there was an ordinance in that particular borough. If you take it down, you can't put it back up. But I still want my cell phone. You know, I still got to surf the web. So what we do? We came in here, we scanned it. This is just like a GPR. You've seen them on TV. If you don't ever use GPR, I'm sure you've seen them on the Discovery Channel when Expedition Unknown's looking for stuff underground. What do you do with that signal? You create that. That's what we found. 1/2-inch tendons were supposed to be equally spaced all the way around and pre-stress, so to speak, or post-tension, and backfill grout. You know, it depends on how you build it. You know, if you put the pipe together and you put the cable in it with a form, that way you pull it together basically. Are you pushing the concrete from the bottom when you pump it full of grout, or are you free falling? Guess what happens when you free fall? That's what happens. Pump from the bottom if you can. Why do you think you pump from the bottom on drilled shafts when you're drilling caissons? You pump from the bottom so you don't mess up your rebar and you fill all the voids. Exactly. Put that in your specs, huh? With the trim. Yeah. Okay. I'm sorry.
What's the one on the left?
Well, same thing. It was just a different section. That's the A leg, which is at 0 degrees. This is 50-foot elevation. You know, we had a whole slice cross section of this stuff, and they were just everywhere. But you know, I asked myself, does it really matter? Because it's just intention. It didn't have to carry compression. I wasn't the engineer record. I just told him what was wrong. I love telling people what was wrong. I didn't have to fix it. I just told them what was wrong. All right, the last topic. I got a little time here. Trunnion anchor rods. This is a technology that I came up with in 2015. No, 2010. 2010. I had a question from the Army Corps of Engineers. Big dams, really big dams. This is a gate called a Tanner gate. It goes up and down and lets water out, in and out. Not in, but out. These gates are held by really big bolts. The next photograph shows these bolts. These are the covers of the bolts. So remove the covers. This is what you got. 2 to 2.5 inch bolts, bunch of them, all pre-stressed to 108,000 pounds to hold that water back. All right, because you got to think, all this water is pushing on this thing. This bolt's got to hold it. Well, these bolts, these are big boy bolts. These bolts, some of them we ran into were 60 and 70 feet long. The problem with the Army Corps of Engineers was having was in the early 60s, mid 60s, when there was one gentleman I was told that came up with this design, and it has been used ever since. But they found some notes. He said, look at these things in 50 years. Guess what? What do you think happens to a high strength bolt that's under 108 kips of tension when it fails? It is the biggest bullet you've ever seen. West Point Dam in Georgia, West Point, Georgia, they were missing some. And they couldn't figure out. Then they said, oh, wait a minute. These cover boxes that are over these things, why are there holes in them? And there became the question. Are these bolts any? So the Army Corps, anybody with the Army Corps of Engineers? I love those guys. I love them to death. And I'm sure there's somebody online. They had the government came out with a really good policy. Put it in the FAR regulations. Don't stand in front of the cover boxes. So we had to test all these things without standing in front of the cover boxes. We posed the question, are they still under tension? What's their tension? And are still in one piece? Okay. Seems simple enough, right? Well, this is just a Tanner gate with bolts. We came in here and we modeled the connections. We did all of that stuff from a mathematical standpoint. This is what it looks like, a trunnion anchored rod schematic. All these bolts go in, they're anchored at the back. They have a trunnion girder on the front, and then they're tension. And they put a big bolt on it. I mean, a big nut to keep it from pulling back into the dam. So I proposed it's a piling, it's a rod. I've always preached that a piling is a rod. Well, this is truly a rod. Why don't we just do pulse echo or do a flexural wave test or a shear wave test? Everything you want to know about a material is in the waves that travel through it. I don't know how to interpret all that information, but all the information is there. Transducer, tap it on the end, bounce a wave back and forth. Transducer, tap it on the side. That thing actually vibrates like a piano string. I mean, a guitar string. And this shows it the best. Tap, flexural wave, bounces back and forth. And that's 70 feet of a rod under 108,000 pounds of tension. And guess what? The frequency or the speed at which this thing bounces back and forth is a function of the tension. It's amazing. To me, it was just, this is how you test it. Sorry for the grainy photograph. It's not something I can show. Impact device, he just hit, notice he's not standing in front of the rods. He's got we took a handle off a 3-pound hammer from Home Depot, sawed off the head, and we touched the rod over here and hit it with another 3-pound hammer. All we wanted to do was excite that little rod vibrating a little bit. And we captured the data. Very fortunate. It works. Sometimes I think we were trying to build watches out of something. They just wanted to know, okay, bless his heart. I had a scientist that worked with us on this, Mark. He wanted, is it 107.2 thousand pounds or is it 109.8 thousand pounds? I don't care. Is it over 105 and is it less than 120? Well, this is your technical part. This is get your PDH off of this. This is a frequency response theme. In other words, frequency, amplitude of the response, all the peaks tell us how much tension is on those rods. As it turns out, the dam that I told you that they were shooting rods, they were failing and shooting out like bullets. Turned out we tested every rod in that dam, and we only found one rod that was less than 120,000 kips, 120 kips. Everything had been tensioned to 130, 140, and the failure was like 160 or 180 on those rods. Who knows if it was, environmental conditions causing stretching and that sort of thing during its 50 years of life, I couldn't tell you. 2 more slides left. I think I'm gonna make it. This is our results. 0% error, minus and +1 standard deviation. What we did, how we determined this was we actually did liftoff test of the rods. We test it, calculate the strength, the tension, then we put a device on it, crank it like a come along, pull it off, the liftoff test to see how much tension was there actually there. So we were real pleased and did a lot of work. Still doing work, my understanding, for the Corps now. In summary, know the end result you're looking for on non-destructive testing, okay? Don't let folks come in and sell the bill of goods that they think they can. I'm the world's worst. Clients called me in my decades of work, said, Dr. Holt, can you do this? My absolute answer was, yes, sir, I can do it. I ain't got a clue how to do it. Don't even know what I never heard of it before. Trunnion anchor rods on large dams, and that question was asked to me. I said, absolutely, I can do it. What's a trunnion anchor rod? That's my solution. Choose the appropriate method for the investigation. It goes without saying. Hire experienced pros, or at least hire the firms that, if they let others do their work, that they're under the supervision of the experienced pros. Always look at your non-destructive testing results with skepticism. I still do, or I still did when I was doing it every day. Do they look reasonable? In other words, I've had many tell me, Darren, these piles are 235 feet in the ground and they're driven piles. I'm like, try again. I've had folks tell me these are timber pilings. They're 125 feet. I say, what kind of material? They'll say southern yellow pine. I'll say, try again. The other person would tell me Douglas fir. That's reasonable. They could be there. You kind of learn where all these foundations are in the country. And remember, field testing or results from testing, any test in the real world, in the laboratory, always tells the truth. It will tell on you if you're doing a test incorrectly or if it's a good test. It will tell you if it's lying to you or if you're lying to it. Results always tell the truth. It might be garbage. That's the truth. It was a garbage test or a garbage application. So with that being said, I know, Patrick, everybody knows, most of you know, some of you in here know how to get up with me. If you ever want to ask questions, I always answer the questions. Call me. Send me an emails. Yeah.
How many of the old wood piling bridges or structures are still around? Where we don't know
A lot.
what actually happened?
A lot. I know.
I mean,
It is wood out of 101,000 bridges in the United States that I was talking about that they had no as-built plans on.
Yeah.
2/3 of them were timber. It just, it's cheap.
And also what actually happened when it was.
Exactly. I've seen it all. I've seen highway departments come in, and when you give it some rotted timbers, they'll cut the rod out and they'll put a 55-gallon barrel around it, fill it full of concrete, put some mechanical linkage. I found one state, and he made me destroy the photographs, but I really have it. But I just can't show them. They had cut all 30 timber pilings out below the bridge, one at a time, put new piling on top of the old piling, and wrapped it in duct tape. Oh, I wish I could show you that photograph. Every one of them are wrapped in, I kid you not, wrapped in duct tape. My first question my first comment to him was, no, I've never seen this before, but why didn't you use camouflage tape? I mean, why silver? It's the darndest thing. Yeah.
That's an interesting fact in North Carolina DOT with all the Helene damage. They're actually reissuing standard plans for timber bridges so that they can replace in kind what was lost.
Right. And it's real quick. It's cheap. When it used to be $5 a foot to buy a timber pile. I'm sure it's 105 now, but it's renewable. Cut it like you want it. Put it up there. It's salt treated or CCA treated. And move on.
There's a lot of timber bridges in North Carolina.
There is.
Trees in the west.
Yeah.
One more
Yeah.
question. Are any contractors using this to clean up Western North Carolina? I mean, the first thing you gotta get is geotech information.
Yeah, I don't know that.
Are they using this?
The system,
Yeah, the system to see what.
they used it up until I left. I don't know. They do use it until you left too. They use it sporadically. I chase red fire trucks now, but I'd love to chase piles again. But I mean, you got to do something when you're tired, right?
Well, I can tell you that they went through the 90s and did some sort of evaluation of all the state of timber bridges. So there are records. That scour report was done on all of those bridges. They didn't go into the detail, like of certain ones. If it wasn't a risk, they didn't bother.
Right.
The ones that were at risk, they did an analysis. Of course, that information is still good because they weren't putting that many new timber piles in.
Right. Right.
So yeah, every time we get a bridge inspection report, it comes with a scour analysis that's
Yeah.
back from those days.
It's at one point in my career, I was testing about 300 or 400 bridges a month. Not me personally, of course. I mean, I was doing a lot. I held contracts one contract went for about 8 years. I'm like you, I have seen a lot of stuff under bridges. I was kept convincing I was going to run into a body one day. I have never done that. Run into alligators, snakes, obviously. I have arachnophobia. Every spider is a killer. Snakes don't bother me, but there's some spiders that big around. I swear they were that big. Alligators, we tested a lot of bridges standing in water, knee-deep water with alligators. It's just get used to it. So it's fun. I had a ball. Makes us not standing up here talking about it makes us like, man, that'd be fun again. Then by the time I get home this afternoon, I'm like, oh, no. Questions, comments, ugly remarks.
But you can't use this technology to determine the condition of the
Yes.
concrete plot.
Yes, you can.
Falling, rusted, corroded rebar.
There's a limit. Generally, if the cross section is reduced by about 20%, you can find it all day long.
Okay.
But little spalling here, little rust there, you can do. I had a project on Mobile Bay in Mobile, Alabama, brand new bridges, 36-inch square, pre-stressed concrete piles, 1,000 of them. They had just put the piling in, and this was in 2001. The inspector came to work literally one morning, and there was a piling missing. You don't pick up a 135-foot, 36-inch square pre-stressed concrete pile and walk away with it. They put divers in the water. They found it on the ground, in the mud. It had been broken during driving. And as a result, we spent 3 months testing every single pile multiple times after they completed each driving operation. I had a ball. I really gained some weight because I had my favorite seafood restaurant down there. But we were looking for damage. And we found several that were damaged. And the contractor had to go in there and put in a sister pile right next to it. And those bridges are still there today. In fact, they're the main bridges that go from over Mobile Bay, from Mobile to towards Pensacola on I-90. So not 90. I don't know. It's down there near the USS Alabama battleship.